is a special seminar, summer seminar. We have Dr.
Bataller.
Bataller. I'm sorry.
No worries.
Dr. Bataller. He's actually over in the physics department here at NC State, and is going to be giving us a presentation today on an area of plasma science that we in our department actually don't have as much of a presence in, but maybe be looking to try to maybe grow in this area one day. We've talked a lot about in our group about trying to get involved more with laser interaction with plasmas, mainly on the diagnostic side. This is a little bit of a twist to that, but at the risk of making sure I don't steal all your thunder, I'd like to introduce our speaker for our seminar today. So please give him a warm welcome.
Okay, thank you very much. It's a real pleasure to be here to give you a talk on a subject that's near and dear to my heart and that I've been working on for quite some time now. So I'm happy to share this with you. Now, a lot of promises in the abstract, so I'm going to try my best to get through this data and these pretty quickly, but such that they're well explained. And I did promise in the abstract a live demonstration for you, but we'll do that after the talk, after all questions are done. So the talk that I'll be giving is entitled Plasma Transitions of Strongly Coupled Plasma. So I like to give credit where credit is due in the early stages of a talk. So a lot of this work was done over at UCLA in the Department of Physics. And some of the work that was done on the MOS2 was done in the Gundog-Do laboratory in laboratory here at NC State in the MSc department. And then the last topic that I'll be talking about today was done in my laboratory at NC State, and that was funded by the Julian Schwinger Foundation. So the outline of today's talk will be plasmas. So we'll talk about what a plasma actually is, and talk about what strongly coupled plasmas are. And then I'll focus in on these three different systems which show an interesting phase of plasma called the plasma phase transition. The third topic will be on quantum phase transitions that you can find in plasmas, and this will be in a very different system. And finally, quite a range in which and show you a discovery that I made just a few months back, and so you will be the first to see it. And in fact, that will be the live demonstration for you. And because I name it, so I just named it gravity crystals. Hopefully you'll see why. So what is a plasma? Okay, so I'm going to broadly define a plasma as a system of unbound charged particles. So I say system because what you'll see in this talk is it's not always just atoms, nuclei and electrons. They can be quasi-particles or so forth. But when we're talking about atomic plasmas, what we typically think of is, let's say we start with ice, and then we know that's in a solid form, and we heat it up. So we add some temperature to the system. When we do that, the bonds start to soften in the solid stage, until finally they start to flow, and then we have a liquid. Heat it up some more, the bonds eventually break from each other, and then they are free to move about into gas. All right, now we really crank up the temperature. Now gas atoms collide with each other, electrons will ionize off of the atoms, and now we have what's called the plasma for now, and I'll show you in the next slide. So if you're not vaguely interested in plasmas, it's okay, but let me say one thing. If you're interested in the universe, you might be interested in plasmas then, because over 99% of the visible universe is composed of plasma. We're talking about stellar systems, interplanetary, interstellar, intergalactic media, all mostly dilute plasmas. Of course, I make the caveat here of visible universe because dark matter's there, but we don't know what it is. So, and that represents much more. So, but closer to home, dense plasmas we can observe are lightning. So that's about 40,000 degrees at atmospheric pressures. And we're completely covered by a plasma in the ionosphere. So lots of plasmas around in the universe and lots of applications. Some of the applications here: launchers and thrusters, and in some you can treat the charge excitations in semiconductors as plasmas. And of course, what talk wouldn't be a talk without the promise of saving the world? Nuclear fusion. So This is the hope of many of the efforts in plasma physics, fusion. And this is, of course, the tokamak plasma, which is at 100 million degrees or so. So this is hot and what I would call dilute plasma. What I've studied over the past 10 years has been strongly coupled plasma. So what's a strongly coupled plasma? So in the dilute systems, we have particles that are at such high energy that they rarely interact with one another. And so that's what we would call an ideal plasma. But when you start bringing up the density for a plasma, you start to have more interparticle interactions. And so we find this by this parameter here, gamma. This is the strongly coupled parameter. What this is the ratio of the Coulomb potential energy to the kinetic energy. So what that says is how strongly these particles are interacting with one another relative to how fast they move. And so when this value, which is given over here by charge squared over their distance in kT, so you can imagine the distance, if you bring the particles closer and closer together, they're going to interact more and they're going to become more strongly coupled. So in the limit where they're really far apart, where gamma is much, much less than 1, you have a weakly interacting system that behaves more like a gas. Cranking up the density, and now you start to have more particle interactions, correlations, and eventually condensation into both a liquid and at very high gamma into a solid. So presentation of this. This is a particle simulation provided by Los Alamos. You can find this on their website, of a one-component plasma. A one-component plasma is just a singly charged species and nothing else. So it's in a box, it's free to move about. And so for gamma 0.1, which is very small, you'll notice that these particles here just move without any interactions whatsoever. They just pass right through the system, acting like essentially a gas. And this is a 3D simulation, and we're looking top down. That's why they can pass in front of each other like that. Now, if we start cranking up the interactions, or not, you'll start seeing that we undergo more deflections. And you'll see that they're moving in straight lines, but every now and then now we start to have more interactions with the particles. Keep cranking it up, and at gamma of 10, you'll start seeing that the interactions start to dominate the whole system. So this is what a strongly coupled plasma is. So here's the universe in plasma form. Come on, have you ever seen a graph that has 40? And so that's density of 40 orders of magnitude, and here's temperature. This is the whole universe, right? Maybe minus Big Bang, all that stuff. But chances are you're going to find it in here, right? So over on this line here, this is gamma equal to 1. This is how I see plasmas these days. Over on that side, you got your dilute gaseous plasmas, and over here, strongly coupled. So you can see your usual suspects, interstellar media, intergalactic media over here, pretty hot actually, but very dilute. And you have tokamaks over here. The sun has many different densities and temperatures inside of it, so it occupies a fairly large range. And really, and pretty high density have nuclear weapons and inertial confinement fusion. And over in this region, you have a lot of applications of plasmas that we use, such as lighting and also in atmospheric plasmas. Now on this side of the curve, we have a lot of astrophysical objects that actually occupy this space, such as the crust of neutron stars within white dwarf and brown dwarf cores, and actually within planets as well, such as Jupiter, and even Earth is expected to have a strongly coupled plasma deep inside. And down here you see something really, really cold. This is a really interesting experiment which I'll mention a little later, but this is almost 10 million using magnetic traps and laser cooling. And you can also get very strongly coupled plasmas by putting electrons on liquid helium. And because I'm in the nuclear engineering department, here for you. To first order, molten salt can be considered a strongly coupled plasma. Now, for this first part of the talk, I want to talk about this one little section here. Little, but again, orders of magnitude, so it's actually a decent amount. I'm going to focus in this little region, which occupies these three very interesting systems, which I had the pleasure of studying as a graduate student. And also in here is lightning as well. And this would be sonoluminescence, laser breakdown, and spark discharges. So sonoluminescence, sound into light. That's what the the name is. Right here is a system that I built at UCLA where you have a bubble that collapses and emits a flash of light. And let me show you a video of that. Right here. So when you have a bubble that's filled with a gas and it's inside of an acoustic field, you can actually make the thing oscillate. And over in this graph, you can see the radius as a function of time of the bubble. And over here on the right-hand side, you have the pressure acting on the bubble. So when you have the bubble experiencing a negative force from the acoustic pressure, it pulls the bubble apart and starts becoming a tenuous gas on the inside. And then, when you have the pressure swing the other way, you notice that the acoustic pressure is high over here and the bubble reaches its maximum, and then it undergoes an accelerated inertial collapse. It experiences a very non-linear collapse with accelerations reaching 10 to the 12 Gs. And at the very bottom of the collapse is a flash of light that's emitted in as short as 50 picosecond timescales. Now what's happening here is that the gas is experiencing an extremely violent collapse, and all the gas inside of it is compressing and heating to about 10,000 degrees and near liquid density. And that is given the nickname star in a jar because when you're in an acoustic system, you'll have a bubble that's trapped, say, in an antinode, and it will be emitting flashes of light at 20,000 times a second, and so it'll just hover there as a point source of light, and so that's why it got its name. And one of the curious things about sonoluminescence is that the emission that it radiates is that of a black body. Now why is this so interesting is because the size of the bubble when it's making the light is only 1 micron. This is very, very small. This is one of nature's smallest black bodies. And so here's the spectrum for a xenon bubble or a helium bubble, and you can see that these are the black body fits are quite exceptional. And this is common. And so there was an interesting thing about this, which was, okay, what are the conditions for a black body? And really boils down to 2 of them. That the system is in thermal equilibrium, and that the size of the black body itself is much larger than the photon mean free path. That means that the light has to undergo many absorptions and re-emissions before it leaves the body. And so that means that if you were to follow plasma theory, that you need about over 10 to the 21 electrons per centimeters cubed for that 1 micron scale. And for these plasma conditions and temperatures, 1 eV and 10 to the 21, this creates conflict. The reason is because based on plasma theory, it should be very weakly ionized, less than 1%. Yet we see this incredible amount of ionization, almost the full level. So there's a conflict in this field, and it wasn't quite clear what we were seeing here. And so I set about to figure out, well, is this actually highly ionized? Are we being fooled? Is this spectrum not actually a black body, but some kind of black body imposter? And so you couldn't really make that, with confidence to say that the emission was a black body. So how about in transmission? Can this black body actually absorb light that's incident upon it? And so that's the experiment that I built, and of course I have a fingerprint for a photo op, unfortunately. That's mine right there. And then to do this, you focus a laser light onto the bubble at the exact moment that it's emitting light in exact space. So this is a bold experiment as a graduate student trying to have laser target practice of a bubble that's moving in space on the micron scale, and you have to synchronize it to 200 picoseconds. So, it was really fun. And wasn't sure what the results would be, but here's a experiment for that, and here are the results. Bottom line, it was successful. We actually were able to couple the laser light into the bubble, and it only occurred when the bubble was emitting light. And that was given by these graphs. So if you see these red dots, this is the bubble radius as a function of time. And over here, this is an indication of the laser plasma coupling. And only when it's at this bubble minimum do you see this stronger interaction occurring. And more than that, we were able to infer that it's actually over 10 to the 21 electrons per cc based on the changes of wavelength between these interactions. And so, indeed, sonoluminescence is a highly ionized dense black body. So then what's actually happening? What we believe we're seeing is actually a different phase of matter altogether. We believe that when you add density effects such as screening and correlations, what you actually find is that this leads to unusually high levels of ionization. And the theory for this is by no means complete, but there is a way to approach this, and that's by adding these corrections to what's known as Saha's equation. Saha's equation tells you if you have a certain amount of temperature and density of a plasma, it'll tell you what the ionization level is. And what we find is that if you don't have any density corrections, you end up with this bottom curve. And this bottom curve is as a function of density. So if you follow along this curve or right around here, yeah, our ionization should be less than 1%. But if you start adding these density corrections to it from screening, you'll find that there's actually two solutions to Saha's equation. And so when you have two solutions, which is represented by this curve, that is actually expected to be a first order phase transition. So that means that these phases can coexist at the same temperature and density, which is here and here. And so what we believe we're seeing is actually a new phase altogether. This new phase is highly ionized, and because it's a new phase of plasma, we should be able to see it anywhere in any other system as long as we reproduce the same temperatures and densities. We should see the same effect. It shouldn't be essence. And so looking through the literature, try to figure out, well, does this exist elsewhere in the universe? And one of the places it does is on the surfaces of white dwarf stars, which actually represent over 95% of the endpoints of the stars in the universe, including our own. Our own star will become a white dwarf. And the sonoluminous plasma has the exact same parameters as the atmosphere of white dwarf. So I'd like to change the name, if I may, to white dwarf in a jar, which is kind of fun. Yeah? General thermodynamic state. So if we can't recreate a white dwarf here, good thing. But we can try to make it in different systems. So here are some of the other systems. So this is one I also built, was a spark discharge. Really good stuff, Benjamin Franklin stuff, right? We get some high voltage across some tungsten and then measure it. And I'll explain what this image is in just a moment, but these are the high voltage electrodes separated by about 200 microns, and here's our plasma. I'll explain why it looks like that. So if we want to reproduce sonoluminescence, how do I do that in this system? Well, in essence, to get to the high densities, you have to compress the bubble, and that also heats it as well. Well, can I just start with a high pressure system? And yes, you can. Start with high compressed gases. You can reach pretty darn high densities. So how do I get the energy in? High voltage sparks. And sparks are phenomenal things because they really focus energy into the system, so there's not much more you have to do than that. And you can do this through high voltage transmission lines. And so now this system offers an opportunity we couldn't do in sonoluminescence, which was not only interact with the plasma, but see if the laser light will actually pass through the spark and measure it on the other side. And so this is what I did. I measured the spectrum and also the laser transmission going through the spark. And what we find is that at early times, indeed, the spectrum is that of a black body. It's exceptionally well fit to that. And also the transmission itself, you'll notice that as a function of time, comes here, and then when the spark's on, it drops down to 0, and it gets completely absorbed. And the nice thing is that this red curve here is actually the emission as well as a function of time. And you notice that they perfectly match each other, which they should if you have a thermal system, and that's via Kirchhoff's law. And again, we hit the same types of temperatures, densities, and we see the same type of response. Completely opaque, and we've inferred a very high density in this system. And the interesting thing is when looking at this system discharges, what we find is in later experiments, the expansion of the plasma itself had a lot of commonality with nuclear explosions. And also there was an interesting phenomena that we observed called energetic limiting. So this is freely available. I'm not flagged for having this stuff. But what you can see here is a nuclear explosion. Now, I don't claim that the plasma deep inside the nuclear explosion is the same one as the spark. Not at all. That's very, very hot, 100 million degrees. What I'm talking about is the surface of the fireball itself. A phenomenon was discovered back in the 1950s with sparks and with nuclear weapons, that the surface of the fireball was always the same temperature, between 20 and 30,000 degrees. Doesn't matter how big the explosion was, it was always the same. And it was uniform in space and time for a large amount of time and space. And what this is actually a hydrodynamic shock front. So what creates the fireball is this intense shock wave that comes out. And that shock wave heats the gas in front of it and creates this dense plasma. And so there's an interesting self-similar expansion relationship for these nuclear fireballs. And this effect was called the luminosity saturation effect. So before I continue and show you in the sparks, I just have a little aside through the literature to look this up. And I came across this paper, really fun paper. And what you see here is an explosion from Operation Ivy. And over here you see lightning. This paper was called Nuclear Explosion Induced Lightning. So indeed, in this particular explosion, I shouldn't say experiment, right? It actually induced lightning strikes. And so I kind of like this juxtaposition because I claim that the fireball here has about the same state of matter as the lightning does. And it's all in the same shot. And I also like this slide because it makes me feel a lot better when I get depressed and I can't publish something in a timely fashion. I look back at this paper and I say, well, this Ivy shot was in 1952 and it took them 35 years to get declassified. So I feel a lot better and then okay, well, it'll get published eventually. Back to sparks. So we observe the same thing in spark discharges. And it happens on very, very fast timescales. We're talking nanosecond timescales. So in this image that you see here, this is data from a framing camera. So what that shows us is the radius of the plasma as a function of time. And as that's expanding out, we see that there's this color here, this blue. It's always the same. And that color actually represents the temperature. So it's always the same temperature in time and space until finally later on it has expanded out. The shock wave has emitted or been emitted from the plasma, and then it starts transparent again. But this is the luminosity saturation effect. And we also noticed that the expansion itself, the fireball, is exceptionally well fit to that Sedov-Taylor expansion, which was the theory that was used to actually calculate the yield of nuclear explosions. And because I did make a promise, I keep my word. Let me go back. The point of this photo is that it is a black body. So the way this photograph was taken was backlighting the whole system with a very intense laser that comes right through, and the only places where you get full absorption is right where the plasma is, and hence black body. Long way around, but there it is. All right. Okay, laser breakdown, really fun system. So what is laser breakdown? I'm talking about taking sources, focusing down to points, stripping off electrons, heating the system, and creating a plasma. So I'm a big James Bond fan, and I really enjoy this photo because it was published in it was filmed in 1964, and the laser was invented only 4 years earlier. So they already had really clever ways of dispatching British spies. Already they're thinking that 4 years after the laser was invented. And the other thing is that there's actually a mistake in this, and I would never, this scene would never happen like this again today because they're not wearing their PPE. This lab would be shut down. OSHA would come in and drag them all out. Now, ultra-fast laser breakdown, what I'm talking about is using really fast, short pulse lasers, 100 femtoseconds, and again, starting with the very high pressure, a compressed gas system, but this time, instead of using sparks, focus a laser light down to a very tight volume so that the energy density is very, very high. And when that happens, electrons will be stripped away from their atoms, and then you have yourself a plasma. And so with this system, I was also able to measure the spectrum through a streak camera, and so resolve the spectrum as a function of time, also in space as well. And again, same similar system. We see at low pressures, we have line emission at early times and in all places. And when you go up to a certain pressure, finally you'll see a very continuous plasma that's well fit to black body spectra. and that gives you a temperature as a function of time. So again, we see the same similar density, temperature, ionization, and opacity. And there was actually something that was new to this, because in the femtosecond world, you're actually accessing timescales that you really, this is the only real way that you can do so. And we think we may have seen a sign of a new transition, a different type of phase. So in laser breakdown, you have an opportunity to use what's known as pump probe spectroscopy. So essentially, take your beam, split it off, use one big part of it to make the plasma, the other part as a probe. So now you can actually go and do time delayed resolution with your transmission. So now I take this and I time delay it, and now I scan across the plasma in transmission. So I actually raster across, so I can see the transmission as both a function of radius and time. And so what's different about this in the street camera is that the street camera can only get a measly 40 picoseconds of resolution, where femtosecond lasers, you get 100 femtoseconds of resolution. So what exists down there? What we found is that there was a really unusual motion to the plasma at the earliest times. At the earliest times, we see that the radius of the plasma is created immediately, but it takes this long period of time. Long in my world is 300, 400 picoseconds. That's a lifetime. So it's taking forever to actually expand out. And so we weren't sure about this in emission. So I said, maybe we're messing up on the emission. Let's do the transmission and actually see if this is really happening. We have the time resolution for that. So we do that in time resolution, the transmission as well, and we see the same thing. The plasma isn't expanding at all. It's just hanging out for hundreds of picoseconds. This should not happen. This should actually expand out immediately because there's nothing holding it back. And so we came up with this thought, which is femtosecond pulses, what's special about them is they come in and they heat up the electrons and ionize the system. But the ions don't couple to the femtosecond laser. So they're not getting hot. They're at 300 Kelvin. So we looked at what happens. Okay, what if we put in for gamma 300 Kelvin and the charge density that we see? We get a gamma of about 70. And a gamma of about 70 is actually expected to be a liquid plasma, a condensed state of it. So this is a two-temperature system. Very hot electrons, which have a gamma of about 1, so the electrons are strongly coupled, but not, by 70. The ion should be 300 Kelvin. So this is a possibility that we actually discovered in a different phase of matter at the very earliest times. It's a pretty off-equilibrium occurrence. Now, there's still questions, of course, such as the effects of disorder-induced heating and if electronic screening actually brings that gamma value down. So it's not quite clear yet whether or not we've created it, but there are signs of it. Okay, so now I'm going to switch topics entirely and go on to a different system altogether. This is what I would call a 2D quantum liquid. So I've talked to you about the strongly coupled parameter, gamma, which is a ratio of the electrostatic energy over the kinetic energy. There's also another parameter that you need to think about when you're reaching these regimes, and that's because it's typically a cold system. And that's a quantum parameter defined by, say, the Fermi energy over kT. So it also works with bosons too, but we'll think about fermions for now. And so this parameter means that once this is 1 or greater, or essentially 1, and larger, you have to really start treating this just classically. And that has different effects. So I'll describe where we discovered this at NC State. So in a semiconductor, if you send in light, you actually excite an electron from the valence band into the conduction band. And that leaves behind a hole. So these aren't real particles. The electron itself isn't even considered a particle in semiconductors. It's considered a quasi-particle because it doesn't have the same mass as a free electron. So we have an electron and a hole, and they will actually have a Coulomb attraction to one another, and they can actually form bound states in semiconductors, and these are known as excitons. And these excitons are really analogous of positronium because they're about the mass of an electron. And so that's where the analogy lies. But the same thing applies here for the excitonic systems as in regards to the strongly coupled plasmas. So if you add more and more and more excitons to the system, they'll eventually ionize each other in what's called a Mott transition. And when that happens, you can go a little bit further and cool it down more. And in the late 1960s, they discovered that this excitation of the ionization of excitons will actually form an electron hole liquid if you go high enough densities and cold enough temperatures, given by this cartoon here. So you can see that these excitons will ionize, they'll be free, and at cold enough temperatures, they'll actually condense into a liquid form. And an empirical relationship was found with the boiling point of the system, the critical point of this liquid, so at what temperature will this thing boil away, and what's known as the binding energy of the exciton. That's essentially how strongly bound these excitons are to one another. So there was an empirical relationship that was found, and what this showed was that for the discovered materials, germanium and silicon, there was about 6.723 Kelvin and a very small binding energy. But then other systems were found, and diamond was one which had the record of 165. Now, you probably don't think of diamond as a semiconductor, but hey, you excite it with 6 eV, it becomes a semiconductor, right? So the question kind of came to a point, because this discovery was great, but it's all cryogenic and we can't really do very much with it, at least in practical applications. It's not nice to bring around liquid helium cryostats. So is it possible, can we find a system where the binding energy is large enough that we can reach room temperature electron hole liquids? And so, does that exist? Yes? I won't spare you any suspense here. We found this in a system what are known as 2D layered materials. So the isolation of graphene won itself a Nobel Prize in 2010, and that brought in a wave of interest in these single layer materials. And one of the single layer materials is called the transition metal dichalcogide. And specifically for us, we looked into molybdenum disulfide. This is a direct band gap semiconductor. And what's interesting about these materials is when they get down to a single layer, their properties change dramatically. And one of the properties of interest for us is that the exciton binding energy goes through the roof. And the reason is this. When you isolate the material away from other pieces of material like this, there's no more material above and below, and therefore there's much the screening that you would have from the material itself is greatly reduced. So much so that the binding energy in this system is a half an eV. Now, a half an eV can get you about 500 Kelvin for the boiling point. So at least in principle, this system should show the phenomenon known as electron hole liquids. Here is to excite the system, get the density high enough, don't break it because it's a monolayer, it's very sensitive, and observe the electron hole liquid. So how do we do this, and what do we look for? So the key signature in EHL research has been looking at the photoluminescence, light into light. So how this works is you excite the system, you excite the electrons in the valence band and bring it up into the conduction band. They relax down, and then they'll emit a photon. And when they do, you can measure the spectrum of it. And what that tells you is where these charges came from in their band structure, and whether or not they're actually in what's called an exciton state, or if they're in the EHL state. And the EHL state was characterized by a really broad spectrum that's deeply redshifted. And so there's good theory for this in the literature already. So we can look to that and just see if it exists. And so this is a relatively simple experiment to send in a pump laser, focus it down to a very small spot onto the sample, because these samples are tens of microns, and then collect the photoluminescence and send it into a spectrometer and a CCD. And so here are the results. At low excitations, we're not creating that many excitons. So it's in this kind of gaseous excitonic state. And you can see that by the spectrum here, which is near where you would expect it for very low fluence. Now when you start ramping up the laser power, you start seeing shifting. And eventually you reach another phase where the system itself ionizes. And that's indicated by this broadening and lowering of the intensity. And finally, you hit this really incredible transition where the whole system flies up and is incredibly broad and is very redshifted. And so once you go beyond this state, the spectrum itself doesn't change, and that's exactly what you should expect to see for a liquid. For a liquid, the density doesn't change, and so the spectrum itself shouldn't change very much. And so that's what we saw. And there was other ways of determining whether or not this was a liquid or not. And one of the ways was to look at the temperatures and see, did we reach the boiling point or not? And so we took care to measure this in about 5 different ways. And what we found is that with laser influence, temperature kept going up, 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 up. And then about 500 Kelvin, so if you look at these curves, this is the radius as a function of fluence. We see that at a certain temperature, the center, which is the hottest part of this, this system, amplitude. And we inferred that hole in the center to be the system that's starting to boil out. And that happened at exactly 520 Kelvin. So a little too perfect if you ask me. I don't like that. But it is what it is, all right? So, and I'm sure there's some error, so I can say, hey, it's plus or minus 10, 20 Kelvin. And we also looked at the densities. So we want to know how dense this thing is, and does it match up to the theory or not? And so what we found is going through this nice, lovely equation showing the intensity of the spectrum as a function of the Fermi energy and other parameters, we can figure out what is the charge density. And I mean, this is a, an integral equation, but what this really boils down to is how wide is it and how far redshifted it is. That's really what it all boils down to. That can tell you what the charge density is. And in doing that, we found that the charge density is 4 times 10 to the 13 per centimeter squared. That's really high for a semiconductor. And so, looking back on these parameters, the Fermi energy over the KT is about 4, therefore it's quantum. And gamma here is about 20, and in 2D, that's expected to be a liquid, quantum liquid. So I have one more fun experiment for you to show you. This is the new thing, the thing that I discovered in my lab, and this will be the live demonstration. So here is Wigner crystallization. So I'm going back again to the white dwarfs. I don't know why my career keeps going back to it, but that's where it's led me. So here's the white dwarf, artistic rendering of it. And inside of here is a crystal. This is a Wigner crystal that I will present to you today. So again, let's go back to that one component modeling again. There's a particle in simulation. So at gamma 50, we see that the particles really don't move around very much. And this is really what you would consider a liquid. When you go up to gamma 150, you start seeing that the particles themselves really don't translate very far from their positions. Only occasionally will they actually move out of where, a localized region. That's called a caging effect. And then when you go just a little bit higher to gamma 175, you'll see that this is the solid plasma, the crystal. This is Wigner crystallization. This was predicted back in the 1960s by Teller, the same Teller as the hydrogen bomb. So he was busy. A lovely demonstration shows that you can't see it, of course, because it's in 2D, but this is actually an FCC lattice, which is for crystallization. So I am not the first, of course, to discover Wigner crystallization. This has been seen before. And just this year, actually, it was confirmed that Wigner crystallization does occur in white dwarf stars. So in the core of white dwarf stars, the ones that are a bit cooler, they have significant density and ionization, and they're cold enough. When I mean cold enough, they're still 10 million degrees, but they're cold enough that they actually will form a crystal on the inside. And again, that was just this year. And that's why back in this was first hypothesized, they said that this was a diamond, a diamond in the sky because some of them are made of carbon. And if you look over here on the other end of the temperature spectrum, you can actually make one of these at 10 millikelvin. And this is done by David Wineland, who had magnetic traps and cooled them with lasers. And at a certain gamma, they found that, yes, indeed, it will crystallize. So the point of this is that Wigner crystallization is a scale invariant phenomena. If you look at gamma, it's a unitless parameter, so it can exist in principle on any scale, on any length scale. And it should exist on any particle system. As mentioned before, a plasma is not just atoms and electrons and ions. It can actually be quasi-particles, or in this case over here at 300 Kelvin, a dusty plasma. These little pieces, couple of micron pieces of dust, pieces of plastic, will get charged up in a tenuous plasma and charged up enough that they actually will repel each other and form a lattice, as you can see over here. So my thought process after kind of thinking about this for some time was, if this is a scale invariant parameter, where are the practical limits of actually creating this? So for the case of a white dwarf star, that's pretty much the low end limit of size. They're only about a picometer apart as far as the ions are concerned. So I don't think we can probably make anything denser than that. What about on the other end? Can we make this further apart? And how far? What are the limits? So this was the question. And in order to pursue this question, and I came up with a few parameters that you need. One, you need to have particles, of course. You need to have some kind of particle in here that you can charge up. So the particles I selected were aluminum ball bearings. So these are spheres that are conducting, and particle confinement. So you need to contain this plasma. If you have particles that are all charged up, what will happen? If you don't have anything confining them, they'll just completely explode apart. That's actually what's known as a Coulomb explosion. So you need to have some kind of confinement to keep it together. In, like, say, the white dwarf stars, the electrons are there also to keep everything together, and also you have this intense gravity. And that got me thinking, wait, can we use gravity? Is that a possibility? So it's not that crazy, actually. A gravity well. What is a gravity well? A bowl. You have particles in the bowl. It gets confined. It can't come out. So if you have many charged particles in the bowl, they want to push each other apart because of their Coulomb interaction, but the gravity well pulls it back. So now we have our confinement. And we need to cool these particles down so that they have a very high gamma. This is easy in this system. It's provided naturally because there's friction. The balls will eventually slow down. And finally, we need to charge the ball. So how do we charge the ball? This actually was the hardest part until I had the idea of using a Van de Graaff generator. Hint, hint. So high voltage. High voltage, you can get lots of charge on top of one of these particles. And if you look at the equation itself, you have the distance between the particles. Well, we can't really do that much with it. I'm not going to make a football field out of this. Not on my budget. And thermal. I mean, I'm kind of stuck here. I don't really feel like cooling anything down or anything like that. KT is 300. But charge is something I can change. And what's beautiful about this equation is that charge squared, that's a much bigger term than the other ones anyway. So in a millimeter size aluminum ball bearing, you can get about 250 million elementary charges on it. So you can get a lot of charge on these things. And you know that if you ever just played around with pith balls or anything like that, you'll see that they'll push each other apart. So here's the realization of Wigner crystallization. I have a 2-inch diameter concave mirror. So it's a pretty shallow mirror, but it's an curvature to it. And I've coated it with graphite so that it is conductive. So the aluminum balls are conducting in contact with a conductor. And I attach that to a high voltage Van de Graaff generator. And then I apply voltage. And this is what happens. And it happens in 6 seconds. And a crystal is formed, all in 6 seconds. I could probably watch this all day, but we're not going to. We're going to continue on. So this is really interesting. There's a lot of stuff going on here, and all I needed was a simple SLR camera to do the analysis on it, and that's because of the time scales involved, the size of the particles. And so really, it's not just crystallization that's happening here. It has actually a real rich, it undergoes a real rich phase space on this path. So at the early stages, there's no charge on the ball, so they're just sitting there. And then you charge them up, and they undergo this kind of Coulomb explosion where they all repel apart. And then they reach a kind of equilibrium where they're out. And then at that point, they have enough kinetic energy from when you gave them that first initial kick that they're actually not really interacting with each other that strongly compared to their motion. And although you might say, well, this is just balls moving around, you just charge them, they're moving around. Is this really a plasma? Can I actually call this a plasma itself? And I would argue absolutely. And the reason is this. What you find is that if you do a sonogram, essentially what's the Fourier transformation of the motion, and seeing is there a fundamental oscillation in there? Absolutely. There was a fundamental oscillation of all the balls. And that fundamental oscillation matched up with the plasma frequency. So, and that is a collective motion of a plasma. So the plasma frequency is actually in the system. You can't see it, of course, because everything's moving around. You can't calculate that in your head and look at it, but it is in there. Furthermore, I know how much charge is on the ball, and I know the motion. So this is a cool system. You can track all the balls. You know everything about the system. You know their motion, and you know how much charge is on them. So you can go and calculate everything. You can calculate gamma. So when you do that, you find that here's our gas phase. It jumps up initially. It has this interesting region right here where it's just rolling around. So this loss in gamma is all, or increase in gamma is all about friction and losing energy that way. It's all in the rolling regime. Over here, we form a crystal, and that crystal happens at a value of a gamma 135. And that's exactly where it's expected to be for a 2D system based on prior publications. And finally, you get into this called stiction regime, where the balls just don't move anymore. And the reason is because they're stuck. This is static friction, where you can't push off your location. So that's where the system ends. Now, the cool thing about this is that, well, one of the cool things is that it represents a whole new class of what I call gravity crystals, and then you can do a whole bunch of things with it. And you don't need this nice, beautiful concave bowl that I bought from Thor Labs for probably too much money. You can use a banged up, negatively curved, bowl-shaped object. So right here is an example of that, Lena's bowl. This is a stainless steel 9-inch mixing bowl. And you can see all these ball bearings in here. And then you can test really interesting phenomena that you would see out where in the astrophysical world, such as mass segregation. So inside of the white dwarf stars, some of them have both oxygen and carbon. And what they expect to happen, and they have data to confirm this, oxygen will actually snow out first, and so they'll actually separate from one another based on mass. And granted, these are still different systems, but the whole phenomena of mass segregation actually happens. So if you start up with an initially mixed up system, these balls, which are copper, which are about 3 times as dense as aluminum, will actually segregate down into the center as you run the system. Also, that question, how big can we make this? I still don't know the answer to that. I know they can be made up to at least a centimeter in scale, so I got really large balls, and I had to do that by actually getting hollow balls. So if you get hollow balls, then you can actually go further and further. And I still don't know where this ends. I don't know how much further this will go. I think ping pong balls are possible. Maybe we can do this in space somewhere and really have fun. But quite large. And even more, you can do other things such as not just test monopoles. So in these systems, they're more or less monopoles interacting with each other. But instead of having it in contact with a conductor, you can actually just place a glass dish that has these aluminum balls in it and put it on top of a Van de Graaff generator. So they're not actually in direct electrical contact. But what it does is an electric field on all these balls. And then what that does is it creates a dipole for each one of them. And so they're all aligned. And so they have aligned dipole significance to semiconductors. And so you have, especially in the monolayer world. And so even though that the dipole-dipole interaction is much weaker over a longer range, it's still strong enough in this system to create long-range order. And finally, the last one that I discovered was what I call a tribocrystal. So you don't even need a high voltage source at all. And this came from the fact that if you ever rub your shoes on the carpet and touch a doorknob, you know that, hey, I got charged up. That's called triboelectrification. So you can get objects extremely charged just by physical contact, just by rubbing. So if you have, well, I'll show you the example of that right here, and I'll save that just for the end, and I'll explain what this is. But this is an example of charged balls that are in that have a long-range order, all in a kind of a shallow dish. So I did make a last promise of an exaggerated number, and I said that the Coulomb energy for each particle If you calculate it, these balls over here have about 5 billion elementary charges on it. So if you put that into our equation for electrostatic energy, that's 2 times 10 to the 12 eV per particle. I mean, that beats the heck out of a white dwarf star. White dwarf star is only like 10 to the 5 or something like that. This is a lot more. Granted, particles are a little bigger. All right, so the last thing, tribal electrification, the tribal crystal. So you can create a type of Wigner crystallization in this. And again, you don't need a really nice dish or anything like this. This is a shot glass. So I got about 1 millimeter size Teflon balls. Cover this with plastic food wrap or saran wrap, and you shake it. You can get all the balls really, really charged up. Very, very highly charged up. I believe almost a nanocoulomb for this system. And that is plenty to cause crystallization. So, I want to say again, this has been my absolute pleasure. Thank you for having me, and I'm happy to take any questions. And then after the questions, if anybody would like to come up and see the demonstration of Alina's bowl, I'd be happy to show you. And also, if you want to take a sample home with you, I brought a few. So thank you very much.
Questions for our guest?
So what I would have, and you might have shown it, I didn't see it, expected for demonstrating that you had a liquid state of the excitons, this lack of long-range order or only short-range order, but I didn't see that you had that. That would be what would convince me
Yeah.
a liquid state.
Yeah, we don't have that data yet.
Okay.
Yeah. You're right. You're right. Absolutely. And other things such as scattering off of it as well. That's kind of that was actually one of the key experiments back in I believe the 70s that really convinced people that it was a liquid. We were kind of going off of the old PL signatures and inferring that way all the analysis. But those experiments still need to be done.
Question in the back?
With gravity crystals on the macroscopic crystals you created, do you have any space for those things? Or they seem to be, I don't know, look like amorphous material science.
Oh my God, yes. Okay, so every time I talk to material scientists, I won't say who, because they look at it and they say that's not a crystal. That's not a perfect crystal. Well, then I ask, well, what is a crystal? And then I get no answer. So for me, and maybe I have the graph of this. No. A lot of fun. Oh, no. No. I know I have it. Ah, here. Right here. So I did analysis on this. So it's a good question, And of course, I didn't do it for the Teflon ball one. It's an imperfect system. Right? I can't charge each ball uniformly just by shaking it. It was just a demonstration. But there is long-range order. And I could do the analysis. And I have done the analysis on the other systems, particularly the one with the concave dish, the one with nice geometry. And what you do, and this is material science 101, so you'll love it. What I do is I do the radial distribution function. Okay? And so that's actually how I was able to figure out whether or not it's a liquid or whether it's a crystal. And you'll see the radial distribution function has a characteristic signature of when it becomes a solid. And you see that nice, long, sharp peak, longer range order. So as a function of gamma here and the distance away from it, you'll see that, balls can't overlap, so this place is nothing. Here's your first neighbor, second neighbor, third neighbor, fourth neighbor. Now I'll ask you, at what point, what peak do I have to make it a crystal? So I'll leave that question to you. You're welcome. Very defensive. I believe it's an FCC. I always get these confused, and that's just my ignorance. I think it's an FCC lattice.
Does that mean that any crystal that is within
I believe
should be
I-
FCC in the end?
I believe so. I believe that's true. And the 2D one is always going to be the hexagonal lattice, which is what's observed. Although I should make a mention that in
Both of them have the cross-packing or the same
Exactly, right. That's the densest structure that you can get. And that makes sense because when you have ions all packed together, none of them want to be next to each other, so they minimize that distance. And the minimum distance is the hexagonal structure. Although I will say, and this actually goes into your comment, which is when you have a curved surface, it's not going to be a perfect hexagonal lattice anymore, just because you've actually changed, you've changed things. It's not a perfect infinite system or anything like that. So the boundary conditions do matter. And that's actually was shown in dusty plasmas as well. Yeah. In fact, that one by the Nobel laureate David Wineland looks like a football. So, and that doesn't have perfect order all the time. Yes.
So to make it an unbalanced system, you ever try one just on a flat surface, just so you can watch all the particles just blow apart?
Well, this one's pretty close, actually. And well, I'll show this one. And the bottom of this stainless steel bowl, Lena's bowl, is actually pretty. But the thing about this system is that there's also a radial electric field going this way. So it actually kind of cheats a little bit and creates its own force that comes inwards. So it actually helps confine it. But I haven't tried that yet, usually because you need the electric field pretty high. And for a Van de Graaff generator, that means you need to get the ground pretty close to the, otherwise the field's just not high enough. In fact, it's embarrassing because I had this idea first with that system that you just talked about. And I'm like, oh, well, then it's just going to blow apart. This is a stupid idea. It's just going to fly away, and then I'm not going to get the confinement that I wanted. And it only took, like, I don't know, 6 months for me to, like, have the idea, oh, we'll just curve the surface. So, yeah.
Have you tried plucking metal balls out with a pair of plastic tweezers and see if you get how it recovers after you?
I have actually gone to schemes where I put it in a glass dish. And the funny thing about a Van de Graaff generators is that if you keep it on long enough, charge will actually flow around the curved surfaces and get on, even if it's an insulator, and charge the balls up. So in the glass dish one with the dipole, so I only showed the dipole one where if I put the Van de Graaff on and off, it'll just fall immediately. It's not charged. It's just the dipole. Maybe I have way too many backup slides. Come on, Bear. Here. So this one, if you keep this on long enough and it's covered by a lid, you can actually get them charged. And then you can take it off, and they'll keep rolling around as a crystal. It's pretty cool. Yeah.
More questions? What? You're waiting for the demonstration?
The demonstration is more interesting if you come up and look at it. And as I said, if I'll never do this again, but if you want a sample, there's a few of you, and you can have it. I will mention one thing. Don't be surprised if it doesn't look impressive today or many humid days in the south. The balls don't stay charged for too long, unfortunately. Well, you're just not shaking hard enough. But in the winter time, oh, that's a stocking stuffer right there.
Any more questions? You can't see the demonstration unless you ask a question.
Oh, okay. Yes, John.
In the situation that you showed, the going from gas to liquid to solid plasma, and
Oh, that's data.
data.
That's data.
Okay, but
Because I track all the ball motion.
I was talking about simulation that other people did.
Oh,
I don't know.
I'm sorry.
They seem like the gas particles when they form.
The particle in a cell. I apologize. Yes. Yeah.
Their density didn't seem to increase.
No.
The scale.
No, you're right, and that's because they're computationalists, so they can tweak the system without changing the density. Yeah. Actually, what they do is, I believe in that one, they just slow the particles down. But since it's a movie, they can speed it up and keep it the same time scale. But if you look at it, particles are just hotter. Good question, though.
I got one. Maybe it's a silly question, maybe it's not, I don't know. What's the difference between a plasma crystal and a metal?
Oh, God, that's a good question. Somebody asked me the same question about salts. Is a salt the same thing as a...
But I mean, they use plasma. You can look at plasmas
Yeah.
And a lot of times, even whenever you're looking at, for example, laser ablation of metals, the
Yeah.
similar equations will apply.
I don't have a very good. It's not a stupid question. It's a very detailed. It's a complex question. Well, I don't think it's stupid. Maybe it is. I don't know. But liquid metals have been considered strongly coupled plasmas, and that's because they're free to move about and flow about. With a crystal, I think it's a little bit more complicated because you have actual bonds between the ions. So it's not just. I don't think it's the same. I don't know though. It's a good question.
Thanks.
Yep.
Joel, did you have anything? Anyone else? Going once? You always get someone going twice as much. Going twice? Nope. All right. Let's thank our speaker one last time, please.